They take it back.
अच्छा प्रोग्राम आज भूल गए पूरा इसी के चक्कर में, क्या करें। हो गया।
विपिन के साथ ऐसा मैंने लेकिन सच है विपिन, मेरे को भी लगा तुम्हारा ठीक है, अपना दर्द चुकाओ, उसमें दारू नहीं है। पानी
का बटन दबा
नहीं तो बच्चा इतना ही पतला निकल पाएंगे आपसे वो भी
बैक टू आए ना बोथ साइड कंट्रोल पे ना हाँ बोथ साइड फिर से करना नहीं नहीं वहाँ पे देख पेज का ये दिया है ना सिंबल आया ना दिया दिया क्या ठीक है आ गया
Yeah, yeah, most of it. Yes, most of it. Yes. So I'm saving this number and waiting.
गुल्ली से
खाना खाया कि नहीं खाया?
खाना खाया
कभी?
ये 1:15 हो गया।
हाँ, पर हम उधर से हैं, उधर गए सीधा ऑडिटर में देखने के लिए कि कुछ शुरू है कि नहीं, इसलिए आप वेट किए थोड़ा देर।
नहीं आज मीटिंग फिटिंग ये और से है, क्या चल रहा है।
Can read the questions directly this nearby table.
That's fine. Shazad, can you hear me?
Yes, sir.
Okay, so we can check your slides if you want to share them. Now,
Yes, sir. मैं स्क्रीन ही शेयर करूँ.
yes. Yeah, I can see your
Alright.
screen.
Okay, fine.
Can you just scroll through one or two slides?
Yes.
No, the slide is not changing.
Yes. Let me do it, sir. 1 second. Let me reshare it, sir.
Okay. Screen is visible to us, but it's not full screen. Now
So
it's
change हो रहा है.
it's working.
Fine. Okay, sir.
Okay. So we'll start in a couple of minutes.
Oh, fine, sir.
A very good afternoon and welcome back to IIT online session workshop on nano sensor and electronic devices.
Class.
And I go.
Research Scholar at Center for Nano or host for the afternoon session. For that, if anyone is facing some technical issue regarding glass installation in the session at 5 p.m., which will be addressed by the technical people regarding all the issues. Moving on, now with great pleasure, I welcome Professor Ravindra Kumar Jha to deliver talk on design and development of transient sensor. Professor Ravindra Kumar Jha earned his PhD degree from Indian Institute of Technology, Kharagpur. He was with Center for Nanoscience and Engineering in IIT Bangalore for his postdoctoral work, where he worked on the development of 2D material and its hybrid-based gas sensor. He joined CSIR Central Electronics Engineering Research Institute, Pilani, in 2020 as a scientist in Nano Biosensor Group, where he worked on industrial projects such as development of NDIR gas sensor system. He is currently an assistant professor in Electronics and Electrical Engineering Department of IIT Guwahati, where his main focus is to develop prototypes of gas and humidity sensor. He has published more than 30 peer-reviewed articles. His work on humidity sensor has been awarded the top 1% citation award from Institute of Physics UK. His work was also awarded MRS Best Poster Award at Material Research Society Fall Meeting 2019 at Boston. He is life member of Electron Microscope Society of India and Sensor member of IEEE. By saying this, I would like to hand over the session to Professor Ravindra Kumar Jha. Over to you, sir.
Yeah, thanks a lot. Thank you, INUP team and Professor Arun and Professor Pamu to give me this opportunity to talk in front of this big audience. So today I will be talking on design and development of transient sensors. And in today's discussion, we will be mostly covering basics of transient electronics, and then transient materials we will discuss particularly from the front of metals, semiconductors and insulators, which are the basic building block of any electronic device. We will see a case study of a chemirestive sensor, which is the main domain of our research since a decade or so, and then we will conclude this talk. So this is our beautiful campus. You might have seen, since this is an online talk, I thought to include this because some of you might not have visited the campus. So INUP is the great platform, which give you the opportunity to visit our Nano Center, which has world-class facilities in fabrication. These are some students associated with our group. Some are postdocs, PhD, masters, and project staffs. They are working towards, some of them are working towards development of these sensors. Our work at IIT Guwahati is totally interdisciplinary. We do basic computational studies of devices. We do a lot of characterization of advanced electronic materials. We do some flexible sensing and basic back-end electronics for our in-house developed sensors. We do independently, and then we are also collaborating at the front of data interpretation, particularly at the AI and machine learning. And we do everything for the sensors that we develop, and that is why the group's name is Nano Sensors and Devices. Moving ahead towards today's talk, let me talk about why we need all these transient sensors. Actually, what we are trying to do is we are trying to move towards a sustainable approach to develop these electronic devices. Okay, so in general, if I talk, the data suggests that 57.4 million metric tons of e-waste were generated only in 2021. Okay, the total is growing by an average of 2 million metric ton a year. Okay, so apart from that, there is over 347 million metric tons of unrecycled e-waste that is lying on Earth only in 2023. Okay. Only 17.4 of e-waste is known to be collected and properly recycled. Okay. Then if I talk in terms of our country, this is the generation of e-waste notice from Ministry of Environment, Forest and Climate Change, which suggests that in the financial year of 2021-2022, 16 lakh tons of e-waste were generated, and this data is exclusive of some of our devices which are lying in our houses dead. We are not reporting those things. So this data may not be a complete one, but this itself is a big data. Okay. Seeing the semiconductor market, which is increasing like anything, and gas sensing market is also following the same trend. Okay, this is also also on a high, particularly if you see wired as well as the wireless gas sensor market is $1 million market nowadays. Okay, so in today's talk we will be discussing the transient electronics, but that is in context of some sensor. Okay, so I think that will give you a more better idea why we are studying all these things. Okay, why transient electronics and what does it mean actually? Okay, so if I go to an electronic store, say I will ask for some sensor which will have a better shelf life and better lifespan. Okay, but then there are some sensors which we don't want to be have very long shelf life or even very long span. Okay, I think after today's discussion, these two type of devices or requirement of devices will be very clear to you that why we are nowadays not much bothered about very high shelf life of these electronic sensors. Okay, of course I'm talking regarding complete electronics, but since this talk I'm trying to bring it in sensors context. That is why I'm giving every time the example of a sensor, but of course this is equally applicable to any other active or passive electronic device or component. Okay. I will come to what is transient electronics later, but if you see, this is the whole requirement of any technology. Forget about the word transient. Okay, you need passive and active devices, including your transistor, diodes, inductors, capacitors. You need power sources like primary batteries and secondary batteries, and then you need antennas to transfer the data and all. Okay. So this is basics of any electronic device. But then talking about transient technology, it is the emerging field that require your material, your device, and your system to be capable of disappearing with minimal or non-traceable remain over a period of a stable operation. Okay, so for example, you utilize all these parameter, all these components, yeah, like you use, inductors, capacitors, diode, transistor, your sensor, antenna, and then power source. Okay, you constituted a system. Okay, you made one system, but I'm telling you that the system has a capability to disappear with time, no, without any trace. Okay, it is not generating any way or any harmful trace. Okay, so basically you are answering the initial 2-3 slides which were telling that the e-waste on earth is increasing like anything. Okay, so transient electronics has this capability. Okay, that it can disappear with minimal or non-traceable remain over a a period of stable operation. Okay, so if I give an example of a sensor, the sensor will operate for a certain period of time. Say, for example, I am working in some industry where I think that there will be a leak of gas. Okay, for certain times. So, for example, I'm using ammonia in that particular industry for say 2 years. Okay, so what I will do is I'm trying to do here is I'm trying to develop a ammonia sensor which has capability to disappear after 2 years. So there will be no sensor. I mean, I don't have to do anything to recycle it or anything. Okay. So transient electronics, how you dissolve it, based on that, it is divided into two classes. One is fully soluble or fully solution soluble transient electronics, which use only the water as a trigger. So you put your complete system in water and it generates some salts which is completely dissolved in water. Okay. Then you also have partially transient triggered electronics, which use other type of triggers. For example, you can trigger it using light, or you can simply provide some temperature, and the transient behavior is triggered, and now it will be soluble in some solvent. It can be water, or it can be some other solvent. Say maybe some acid as well. Okay. In today's discussion, we will be mostly talking about solution-soluble electronics, because partial transient triggered electronics can bring several other parameters which may not be able to covered within this much time. Okay. So since we are discussing electronics, transient electronics, let's quickly see transient materials first, then we will come to devices. Okay. So transient materials are a type of material with transient behavior that in regular use can maintain their full characteristic and functionalities to meet reliable performance. But when a solution trigger is applied, the material will either physically or chemically disappear completely in a totally or partially controlled manner. Okay. So we will be seeing this whole idea from a integrated circuit perspective. Okay, so consider this basic, layout of an integrated circuit, which you can see that you have different level of interconnects, like local, intermediate, and global interconnects. Okay, so if you see the whole IC, you have semiconductor, you have metals interconnects, and then you have various dielectrics being used at various level of integration. Okay. Similarly, if you talk from a sensor point of view, a basic sensor and a receptor, and you have a backbone, like you have a big electric circuit associated for signal processing and other things. Okay. So if I'm taking just transducer and receptor, it transducer you can fabricate by various lithography techniques. LTCC is nowadays a good technology, and then you have various printing technologies. Okay, receptor materials also there are. So mostly, if you see, the transducer class is basically the metal part that we are discussing. Mostly, you will find that these transducers are built up of some gold electrodes or say platinum electrodes. So mostly metals you will be using as a transducer. Then you have receptor materials, okay, where you use various semiconductors, mostly metal oxides, which are wide bandgap semiconductors, and then graphene and its derivatives like graphene oxide and reduced graphene oxides, and then you have beyond graphene 2D materials like transistor metal dichalcogenides. Okay, and then you have various technologies to form this film on some substrate. Okay, so your receptor material in semiconductor and the substrate on which you are fabricating this are basically insulator in nature. Okay, if some of you are working in this area, you know that you also make your devices on SiO2 substrate and not on silicon substrate in a conventional electronics. Okay. If I do anatomy of a sensor, I will find all these things. I will have, gold electrode, sensing materials, and then you have,
You may continue, sir.
He muted, he got muted. Jasser got muted.
You unmute.
No, we can't. We can't usually unmute or mute a speaker.
So what do you do? You mute all and then unmute all?
No, we don't have to mute all. Only that guy got muted. I don't know, sir. Must by mistake must have muted himself. Shall we call?
Yeah, sir. You are not audibly.
yes. Can you hear me now?
Yeah, we can hear you.
Oh, okay, okay. I think no, I did not do anything. I think someone has muted me. Someone want to silence me. Okay, that is fine.
So there is a request to all the participants. Please make sure that your mics are turned off. It is causing problems to the speaker also. We have to mute everybody, find the person who is actually speaking and then unmute. So this is a big problem. So please make sure that your mics are all turned off. Sir, please continue.
So from where I was, this slide I explained. Did you
Yeah,
hear?
from here you can
Okay,
continue.
okay.
Yes.
Okay, okay. Fine. Thank you, sir. So if I discuss the basic sensors building blocks, I will have, as I was mentioning earlier, that I will have a semiconductor, metal, as well as insulators. And if I will have these three kind of materials in transient electronics, I can build a complete transient device. Okay, that is the whole idea. Okay, so if I what we will I will be doing is I will be discussing first transient metals, and then transient semiconductor materials, and then I will discuss insulators, and then give an example of a gas sensor built using these materials, and then we will conclude. Okay, so some of the identified transient metals are all these that is on your screen: magnesium, zinc, iron, tungsten, and molybdenum. Okay, so these five are the transient metals that has been identified. Okay, so these metals are important to biological functions and can be used in biomedical implants. Okay, so the idea is you make some say passive elements, or even some active devices, and if needed in the body as a cardiovascular stents, or say even screws for orthopedic fixation, you fix in the body. And when its work is done, say for example, the orthopedic fixation is complete, your bones are joined or something. Okay, you then there should not be any operation to remove all those things. Okay, so they are transient in nature, and when their work is done, they will disappear. Okay, magnesium is one of the important metals that is being used for such application. Okay, but not only magnesium, but magnesium alloys and iron has been used in the design of bioresorbable implants such as vascular stents, due to their good biocompatibility as well as their favorable mechanical properties. So these are some figures that you can see, which are used for biodegradable micro clips, biodegradable orthopedic implants, wound closing devices. For these applications, these materials is already being used. Okay, I have one slide on one company's product also on transient electronics, but I forgot to include it here. Okay, so no worries. Let's discuss some of the parameters that we look for in a metal for a transient electronics. Okay, so this figure shows changes in resistance and in thickness as a function of time for various metal thin films. Particularly in this slide, you can see magnesium and zinc, which has initially a thickness of 300 nanometer, and the axis here shows your time, and the y-axis is R by L, your resistance divided by the thickness. Okay, and if you see, what we are trying to do is we are trying to dissolve these films in water, as well as in some body fluid simulants like Hank solution, whose pH can vary between 5 to 8 at a body temperature of 37 degrees Celsius. Okay, so if you see these two curves, what we can see is magnesium. If you see, if you keep for longer time, this R by L is increasing above 100. Okay, we will see what it means. Okay, but for magnesium films of this much thickness, if you keep it in hand solution, the time taking time taken by this R by L to reach above 100 is very less. Okay, just 0.1 hour or something. Okay, similar trend is also followed in zinc with little bit of deviation. Okay. So for this kind of graphs, what we do is, or for this kind of metals, to bring every parameter at one stage, we have defined one parameter. We call it electrical dissolution rate. Okay, so electrical dissolution rate is defined by converting change in electrical resistance to an effective thickness, which are described to which are used to describe the transient behavior as a function of time. So mathematically, EDR can be defined by converting change in electrical resistance to an effective thickness, which is non-physical. So R can be equal to R0 H0 by H, where R0 and H0 are the initial electric resistance and initial thickness of the magnesium or zinc film that you have seen just now. Okay. You have different reactive diffusion model for EDR predictions, similar to the Deal Group's model you might have seen for thickness prediction. Similarly, you have various reactive diffusion models for EDR prediction. For some material, it is not possible to have reaction diffusion model, for example, iron, but we will be not covering that. But for these kind of materials whose behavior is not captured by the model, the EDR is estimated by dividing the material's thickness over the time required for complete loss in conductivity. And for complete loss of conductivity, we consider R by L greater than 100 ohm per mm. Okay, so now coming back again to this this graph, you can now correlate it with EDR. Okay, you can now correlate this R by L greater than 100 with the EDR. Okay, so now you can easily say that dissolution of magnesium in DI water is slow, as well as of zinc is slow as compared to the Hank solution, which are nothing but simulant for body fluid, and these are some salt solutions. Okay, so I think this should be very clear to you. Okay, from the previous graphs, we can conclude that Mg and Zn, Mg alloy also follow the same track, exhibit higher dissolution in Hank solution than in DI water. Okay, and this was the graph that I'm recalling here. Okay, this is the data for electrical dissolution rate in micrometer per hour for different metals and their alloys. Say this AZ31B is a magnesium alloy in DI water as well as in Hank solution. Of course, they also depend on temperature. So at some places the temperature is also mentioned. Okay, but that's not always good. So you never want some materials which is always good, which has high EDR in only Hank solution. Okay, so magnesium and zinc has very high EDR in this Hank solution, but what about in water? Okay, so molybdenum shows an opposite result. The EDR in DI water is higher in MO. As compared to Hank solution at room temperature. Okay. Similarly, for tungsten, the EDR in acidic salt solution is much lower than in more basic solutions, which you can see from their R by L ratio graph in these two figures. Okay, you can see that CVD grown molybdenum and CVD grown tungsten of thickness 40 nanometer and 150 nanometer, how they are dissoluting with time. You also have to see the X scale, because that is very important for Mg and Zn. If you see that the X scale is 0 to 1.2 hour, while for molybdenum and tungsten it is in 100 hours, so 0 to 250 hours. Okay, so that is the massive difference between the behavior of magnesium and zinc based metals as compared to molybdenum and tungsten based. But that is not always always true. I mean, these rates will not only depend on what kind of metal it is, it will also depend on how they have been deposited. And apart from that, there are various other parameters which is beyond the scope of discussion today. But say this is one example where it has been proved that CVD deposited tungsten has an order of magnitude lower EDR than the sputter tungsten of the same thickness. Okay, so sputtering, you know that it is a physical deposition method, whereas the CVD are chemical deposition methods. So chemically deposited, tungsten has much lower EDR as compared to the physically deposited tungsten. Okay, so so these different rates you can tailor and use it for your particular application. Okay, we will see when we will conclude this metal slides that how how this rate EDR difference can be used, or tailored EDR can be used for your desired application. Okay, the transient test you can do in your own lab. Say, for example, it has been demonstrated for Mg that how uniform dissolution in DI water takes place. Okay, so this is the Mg structure that the researcher has started and dissolved in DI water with at different times. So this figure B is at 0.7 hour. This is at 1.4 hour, and then the last figure is at 3 days. Okay, so almost, if you will see, there is a change in at the nano scale. There are change in surface properties. Okay, so with time, different micropores have developed in this materials, and this is equally true for other materials. The study that I'm showing you is for one material, but this is equally. If you see this Mg on the nano scale, micropores has developed. The surface has become rough. The roughness you can see from figure B to figure C, it has evolved a lot. Okay, and needle-like structure has formed. If you see the same images just beneath it, you can clearly see that. Okay. If you study the XPS and other things, people have found that the needle-like dissolution products were Mg oxide derivatives, including MgO and MgOH2, and that is what exactly we wanted. Okay, we want this to be completely oxidized and form MgOH2, which is easily soluble in water. Okay, so various studies can be done on this kind of material. Okay, so in the study, it has been found that MgOH2 is the major product of Mg corrosion in HANG solution, while in DI water, somewhere MgO as well. But both are thankfully very good dissolvable in DI water. Okay. Similarly, there were, the MgOH layer thickness has increased as the dissolution has proceeds, and that is what you actually wanted. You started with the Mg, and you wanted this to be dissolved completely. So MgOH2 is something which you want to increase. Okay. And due to their high solubility in water, these salts products are easily dissolved. Okay. As I have mentioned earlier, that other metals like tungsten, zinc, molybdenum, they also follow similar transient behavior in these water and HANG solutions. But then it depends on the metal and how fast it is dissolving. So, for example, you have seen in last example that tungsten and molybdenum are something which dissolve, and it takes about 250 hours or so to dissolve say 40 nanometer of tungsten, but that is fine. Okay. So key takeaway from these studies is, in general, Mg and zinc undergoes a fast transient behavior in DI water and biological solutions. Okay. While tungsten and molybdenum follow slow but predictable degradation rate. You can predict that what will be its thickness because it gives you a good amount of time to analyze your result. Okay. So this behavior provide multiple options to meet the various requirement of degradation time for different applications. Okay. For a slow transient requirement, for example, medical devices that we have discussed, the wound healing or say the stents that you have seen that require metal to have direct contact with biological tissues for signal sensing, tungsten and molybdenum can be selected due to their slow and controlled degradation rates, while the rapid transient requirements such as secure electronics and for military applications that need to disappear with a limited time range, magnesium and zinc can be considered. Okay. So metals, we have seen that for different applications, you have existing transient metals. Okay. The conventional electronics, we know that they use non-degradable substrates like silicon, gallium arsenide, and all these things. For flexible and stretchable devices, you use PET, PDMS, polystyrene, these kind of things. Okay. Transient substrates are mostly water-soluble polymers. Okay, so these polymers are substituted or incorporated with some hydrophilic groups into their backbone that can be dissolved or disappear or even at least swell in water. Okay, so PVA, PLA, PCl, PLGA, these are some good water-soluble polymers. Okay, so people has tested these things, and some of the tests are shown at your screen. This PVA, PLGA, and POC tests are shown over here. If you see, PLGA took largest among them time to dissolve, say like 2 days at least. Okay, but however, PVA just you need is about 1800 seconds to completely dissolve it. Okay. And then you have some, you may also need some elastomers, like in flexible or stretchable electronics, we are using PDMS. Okay, so you have biodegradable elastomers also present in for the flexible or stretchable transient electronics. Like you have POC, this 1,8 octanol co-citrate that you can see, the polymer of this, as your elastomer for stretchable substrate. Okay. However, the advantage of POC is that it can also be served as an encapsulation material for protecting the device that you have just fabricated on this surface from the ambient environment. Okay. But not only the water is, not only polymers, the substrates for water dissolvable polymers are available. You have some acid soluble polymers also. Like, for example, this PPA. PPA is a which is, you can say that it is a typical metastable polymer which can be self-depolymerized. You might have heard about self-polymerization, but it can be self-depolymerized back into monomers once you have triggered it with some specific stimulus, for example, very specific acids. Okay, so you can again generate your polymers. Okay. Then, apart from that, you have different green materials, okay, like cellulose, silk. There are various green materials that are available. Several groups, including we, have used silk polymer as a biodegradable substrate to integrate with the existing silicon semiconductors to fabricate basic electronics. Okay. So when I say bioplastics, it should be made up of organic, bio-based, biodegradable polymers, right? So biodegradable, flexible materials, using the base materials, say for example, starch, pectin, lignin, silk, fibrin, these kind of materials. Okay, but however, if you see the conventional silicon wafer on which the conventional silicon electronics is based starts with quartzite, but that is the initial thing. You have to have metallurgical silicon, you have to have electronic grade silicon, then you have this Chokalski method through which you pull out your single crystal silicons. Then this is only one part, the crystal growth. Then you have a lot of post processing like shaping, slicing, lapping, etching, polishing, cleaning, and then inspection and packaging. Okay, so all these processes has to be similar to this, has to be post processing, has to be developed for the bioplastic based substrate. Okay, what I am showing right now is without this, so you can consider that this is the just first step, which is we call the crystal growth. Okay, so we have used cornstarch as a base material, and branched long chain of the monomer of the corn starch has been broken by addition of vinegar into branches to reduce its rigidity. And then we have done some addition of glycerin and PG 4000 plasticizer, and done some post process treatment to get this kind of polymer substrates. Okay, we have also integrated silk into this cornstarch based substrates. You know that silk fibers are largely made up of two proteins, which are fibroin and then sericin. Fibroin being the main fiber of the silk, stuck together by a gum coating of sericin. So the degumming process and the making of the silk mesh over the surface of the bioplastic substrate is what we have done recently, where we have added the various thermal stability, mechanical stability, mechanical toughness of this substrates. These are some results of thermogravimetry analysis and stress versus strain curve and the toughness measurement of this film. You can clearly see that bioplastic having silk meshes incorporated is much tougher as compared to the simple cornstarch based material. Okay, and that is also shown by the Young's modulus and the tensile strength of the material. Okay, we have also tried to study the biodegradability. We have also tried to do the biodegradability test. The bioresorbability test is still pending, that we are trying to bring soon. Okay. So these are some results on your substrate. Okay. Then talking about the semiconductors, you have good amount of semiconductors available in the market for the transient, which is having the transient behavior. But today we will be mostly discussing on silicon nanomembrane, because we are discussing this transient electronics in context of CMOS, existing CMOS technology. Okay, so the current silicon membrane, or the current silicon wafers, that you cannot dissolve in something, but what you can see, the dissolution mechanism is present in single crystalline silicon nanomembrane. Okay, so single crystalline silicon nanomembrane has these transient properties. Okay, the mechanism has been demonstrated for large area uniform hydrolysis on the silicon nanomembranes, and the dissolution rate can be controlled by wide range of aqueous solution with different pH values. Okay, so this DI water and some other kind of solvents can be used. Water-based solution can be used for hydrolysis of silicon nanomembrane, and it can be a very. I mean, you don't have to move from silicon. It provides you. You know, silicon nanomembrane can itself be a very good semiconductor material for this transient material. Okay, transient devices. Okay. So people has developed transistor devices. They have also developed all kind of active and passive devices. Some of the results that I will just show you. These are some of the devices that has been fabricated by transfer printing. Transfer printing, if you know, is a technology where you fabricate your device by conventional photolithography or conventional lithography, and then transfer the device, fabricated device on a flexible substrate. Okay, so this represents a schematic of an array of transient monocrystalline silicon metal oxide field effect transistor or MOSFETs after it had been released from the substrate and was integrated on a silk substrate, which is nothing but a flexible substrate that is people are using for biomedical applications. Okay, this characteristic of this transistor that has been fabricated is shown over here. It shows the change in electrical properties of the MOSFETs that you can see. Okay, when combined with transient circuit components, the transient technology can provide more diverse functionalities. Okay, so this paper recently appeared in a journal where you can see I have given the reference in my slides. You can see at the end, or I can share that. Okay, the complete set of devices on the same chip. Okay, so you can see the MG-MGO inductors, MG-MGO capacitors, silicon MGO-MG transistors, MG resistors, silicon diodes, and metals as MG interconnect on a silk substrate. Okay, so you see so this scale represents this 2 mm. So this is not to scale. So if you see, I mean, you have all kind of device on a single chip. So you have transistor, you have diode, inductor, capacitor, resistor, everything interconnects on a silk film. Okay, then these are some other results which has been packaged as well in a uh, as on a silk substrate. There can be the whole circuit was able to dissolve in DI water within 10 minutes or so. Okay, I was talking about some transient sensors. These were some example of transient electronic device, the complete chip. Okay, so let's quickly see the transient sensor part, and then we will conclude this talk. Okay, so what we have tried to do is we have tried to use this biomaterials. I mean, metal oxide derived from some biomaterials. I will not go in the characterization of these materials. Okay, I will directly go to the results that we could obtain on these bioplastic substrates. Okay, of course, these are not fully dissolved. These are partially dissolved transient materials, and we have to trigger with something else as well. Okay, however, the results were on the substrate part was very promising. We could keep the device we could test the device at 50 degrees Celsius, also keeping the bioplastic intact. Okay, so these were some tests on the bioplastic that we have just seen. We could test it from 0.5 ppm to 2.75 ppm to stabilize this currents that you are seeing some fluctuations. We are trying to work on that. Okay, the device were very much repeatable, and we could detect to very low concentration of NO. I mean, this is really plastic. This is what you could achieve by conventional electronics as well. Okay. Yes. We could test these devices at even 5 volt as well as 12 volt or so. We have also tried, but crack down in the in the device. Okay, and this was the result that we could get on bioplastic silk substrate, and the fluctuation that we were obtaining. We have we are still investigating that, but we have formed on bioplastic is not I mean, completely adhere to the substrate. So we have to do some post processing, or some we have to do some plasma treatment or something to achieve some kind of good adherence on the bioplastic substrate. But on the bioplastic silk, we don't have to do anything, because this meshes has introduced some kind of micro micro channels on the surface of this bioplastic, which has helped us in providing some kind of adherence to the sensing material. Okay, so these are some results for NO gas on the bioplastic silk substrate. We could also do some bendability test of these devices. So we try to fix the sensor, and we are trying to test it with some metal contacts, but we are also trying is printing these molybdenum contacts on the surface, and then we as I have mentioned that how you are depositing this metal also has impact on overall EDR. So what we are trying to do is we are trying to test the EDR of this molybdenum contacts by printing method, by inkjet printing of molybdenum inks. Okay, so these are I mean, we will not discuss these results in detail, but just I wanted to show you is devices on this substrate can be easily made similar to any flexible non-degradable, non-biodegradable, or non-bioresorbable substrates. Okay, so to conclude my talk, I would say that a lot of opportunities in the area of sustainable, bioresorbable, and transient electronics is available. We have seen one example of metal oxide sensors, I mean, on biodegradable substrates. Of course, this is not complete transient. We have to look for some materials, some semiconductor materials. We have to test their bioresorbability, particularly. Metals, we have a lot of options, similar options. I mean, people are looking for in semiconductors. Then the substrates that we have seen was bioplastic silk, which is again a bioresorbable material. We have seen at different potential, the material was able to sustain. And these were based on some of our work, which has been recently published in coordination chemistry and this SES sustainable chemistry. And then I would like to thank all of you. Wonders can be done together. We have to join our hands to work. We need people from biological backgrounds. We need people from chemistry. We need support from material science. And then, we could build such electronics. Okay. So with this, I would stop. If you have any question, you are welcome.
Thank you, sir, for this wonderful session. Now we'll begin the Q&A session. Sir, the first question is, can we make biodegradable solar cell? The participants.
I think Professor Arun can answer that, but I think there are some reports on since I'm talking about complete transient electronics. What I could understand that in solar cell, what you need is again the same kind of materials, right? You need metal contacts, you need semiconductor, which can generate electron hole pairs in presence of some photons, right? And then you need then separation of these charges and all. I mean, that is what solar cell would look like. I mean, then there are experts, but I think there are reports on biodegradable solar cells, but I'm not sure. But I think if they are making complete electronics, the solar cell is not an exception out of that. Okay.
Thank you, sir. The next question is, if these devices are soluble in water, their performance will be affected if came in contact with moisture.
True. That is true. That when it is coming in contact of moisture, the performance may degrade. Okay. But say for example, if I say a wound monitoring device. Okay, so I'm trying to make some patch which will be fixed on the wound. Okay, so then you have a layer of substrates which can be made again, little bit what you say. I mean, say for example, I'm giving you one example. I want a wound monitor device. Okay, and I know that as I have told you that these devices should operate in a certain range. Say for example, I want my device to work within 7 days. Okay, or say 15 days. Okay. So of course, I have to design such devices considering the moisture, in moisture content in which it will work. For example, the wound, maybe my device is seeing say 80% RH. Okay, and apart from that, it is seeing 90% RH in the ambient also. Okay, so I will make my device in such a way that it can sustain that for at least 7 days. And that is what the whole idea of transient electronics is. You don't want your device to be moisture resistant, or you don't want your device to be water resistant, but what you want your device that your device should work at least for the desired time period perfectly. Okay, so of course they will be, if I summarize what I have told, that it will be hampered by the not only humidity, but it will also be impacted by the outside temperature. It will also be impacted by other ambient conditions. But then the whole idea is to dissolve this devices within the stipulated time. So if I am commercializing some technology, I have to test that this device should work in that particular time frame. Okay. So you are right that it will be the performance will be hampered by the moisture and other things. But yeah, the sensors are made like that. Okay.
Thank you, sir. The next question is, what is the thermal stability of this transient electronics?
Thermal stability, whatever dissolution we have seen, was at body temperature, 37 degrees Celsius or so. But with the time, the dissociation or the EDR value. I will take EDR to explain this question. So if I will increase the temperature, say for example, if the body fluid, if I'm going beyond body fluid temperature, say I'm going to 40 degrees Celsius or so, okay, that the EDR value can increase or decrease for particular metal or particular semiconductor. Okay, but then these devices are usually made for the operation of at near room temperature or say these devices are not usually not operatable at very high temperature. Usually you can expect at 22 degrees Celsius to 50 degrees Celsius, not beyond that. Okay, I mean, this is what the technology will emerge. For example, if you see the silicon nanomembrane, it can sustain very high temperature, but this molybdenum can sustain very high temperature. But then if you since you are talking about a complete device, your polymer may degrade at 22 degrees Celsius. So in the complete device, you have to go ahead with the weakest among them. Okay, so it's not that device can, the materials cannot sustain. Some of the materials can sustain very high temperature. Okay, but when you talk about the complete device, the performance you can see is will be really hampered by the temperature. But yeah, if you talk about these devices, they are mostly nowadays being targeted for human body application, and that is what 37 degrees Celsius or 35 degrees Celsius is what people are trying to operate these devices. Okay.
Thank you, sir. The next question is whether the transient materials are compatible with existing materials.
Yes, they are very much compatible. For example, if I talk about molybdenum and tungsten, we in electronics also we are still using in our labs for contact preparation or interconnects. Of course, industry use some other grades, but at laboratory scale we are still using. Even in industry also. For sensors and all, I'm not talking about IC fabrication, but in general, in microsensors and other devices, these metals are pretty much being used. And then silicon nanomembranes is, of course, the name is only silicon, so it is very much compatible with the CMOS technology. Okay, and the polymer substrates that we have seen are mostly, similar materials we are using for flexible electronics, and you know that flexible electronics is now has established itself as a parallel technology to the existing CMOS technology or silicon electronics. Okay, so you can consider that these devices are pretty much compatible with the current current silicon technology. Okay. But of course, these are in initial phase of it will take some time to evolve these devices. Okay.
Thank you, sir. The last question. When this transient electronics are dissolved in any solvent, are they hazardous? And if so, then how to discard it?
No, see, the whole idea of transient electronics, I think I could not explain the definition of transient electronics clearly. Bioresorbability is another term that mostly, we use in as a synonym for the transient electronics. Okay, so these the whole idea is of transient electronics is that the byproduct should not be a hazardous. For example, this molybdenum strand or say magnesium strand, when inserted into into our body, the idea is after its operating period, say for example 1 year, it should make some salt, and even it can go to the blood. And there are some tests that it has been proved that they are not harmful at all. Okay. Similarly, the patches of wound monitors that I have discussed, the whole idea is this patches will be put on the wound, and over that when its functionality is over, or when its time period is over, this patch will be dissolved on the wound itself, or it can be washed away in water. So say for example, you have seen that Mg is dissolved at MgOS2, which is not at all harmful. It doesn't have any toxicity value. Similarly for molybdenum and this polymers also. So the idea of but transient electronics is that without generating any bio waste, even in phase of that is why this bioresorbability, when I say it is it has to be compatible with our body, with the it has to be the idea of bioresorbability is that it will be resorbable in the body of human, or wherever it is being tested. Okay. So I don't think that anything which is generating some harmful end product after dissolving, even in not only in a DI water, but say even in Hank solution or in any acid, if it is generating some toxic end product, then we can call it transient electronics. It is the whole idea is to have non-toxic end wastes. Okay.
Thank you, sir. The next question is, what are the main limitation and performance barriers of transient electronics?
Main barrier in my opinion right now is is the deposition techniques that are available. So, and for example, say I have, I'm sorry. Say I have a flexible substrate, the polymer that I was talking. Okay. Or say some elastomer, say POC I'm having. I want to deposit silicon nanomembrane, okay, in one system, and I want to deposit say molybdenum in one system. Okay. I have to bring my substrate to these two places, where I don't know that if I have to, play with the substrate temperature for getting better adherence also. Okay, so if I will increase its temperature, say for example, 70 degrees Celsius or 80 degrees Celsius, I don't know how this POC will behave. Okay. So in my opinion, I think the how we are depositing these materials, if that can be streamlined, then the transient test that we do is standardized over the time. I think then these devices will emerge like anything. But it is already, some market players are already there. They are already trying to bring some bio implanting materials or bio implanting devices. So the I think the technology is maturing over the time. Okay.
Thank you, sir. The next question is, can we use this device for in vivo monitoring?
Yes, I think the bioresorbability is all about the in vivo monitoring, and when I say biodegradability, then in vitro comes. So yeah, I think in vivo monitoring already these devices can be are being used. Okay.
Thank you, sir. The next question is, with this device, how can one calculate humidity sensing parameters with time?
Okay. So what is the question?
So, how can one calculate humidity sensing parameter with time?
क्लास में ये वर्क्स हो गए थे
Humidity sensing parameters. I don't know. Are you able to hear me?
Yes, sir. Yes, sir. Yes, sir. You're audible.
So what I could understand from the question is I mean, in terms of sensitivity, something has came in chat box. Let me. Can I see that? Yes. Yes, Mukul. Could you please provide comments on characteristic of no, not this. Yeah, this. With this device, how one can calculate humidity sensing parameters with time? Mohini, can you quickly tell what do you mean by humidity sensing parameters? Do you want to make a humidity sensor with this material, this device? In terms of sensitivity, with this device, how one can calculate humidity sensing with the time in terms of sensitivity and sensing response? Okay, let me reframe this. What I could understand from your question that you want to do basically humidity sensing itself with this kind of device, right? If that is true, what I can say that as I have shown one example of NO sensor, which is a chemical sensor. Similarly, you can also design a physical sensor. I mean, humidity sensor is basically a physical sensor which if I'm talking about resistive or capacitive humidity sensor, you will have very similar device structure where you have this metal electrodes as your transducer, your sensing film, or it can be a dielectric in case of capacitive devices, or it can be, say, for example, semiconducting if you are using a resistive device, and then your substrate. So we have discussed all these things, metal semiconductor and insulator. I mean, that is why I discussed the complete transient electronics initially before we actually saw some gas sensing devices. So that, I mean, if you have basic understanding of these devices, and if you understand the how humidity sensing works, particularly the relative humidity sensing one, I think it is not difficult to design a humidity sensor with this kind of existing technology. Okay, so if I go in a little bit more detail, if you see the current humidity sensors, mostly they are either based on conducting polymers, or you have metal oxides like Fe2O3, or you have 2D materials like we are also working on since long on tungsten sulfide based humidity sensors. Okay. So yeah, I think you can easily design a humidity sensor based on transient materials. Okay, since all kind of materials are available here. Okay.
Thank you so much, sir. I request you, sir, to respond to the remaining question in the chat box. And thank you very much for this wonderful session.
The last question, this Mukul Kumar, could you please this question?
So you can address those questions in the chat box.
Oh, okay, fine.
Yes, sir. Thank you so much, sir.
Thanks a lot. Yeah.
Yeah, session.
The next talk is about device engineering for deep UV photodetectors using gallium oxide by Professor Ankush Bag. Professor Ankush Bag, are you present? Hello.
Yeah, am I audible?
Yes, sir.
Yes, sir.
Okay, you can share your screen.
Yes, sir.
Dr. Ankush Bag is presently working as an assistant professor at IIT Guwahati since December 21. After completing his 5.5 years at IIT Mandi, he completed his PhD from IIT Kharagpur in 2016 on gallium nitride devices, including epitaxial growth, application, and characterization of gallium nitride. AGM presently his research interests are ultra-wide bandgap semiconductors such as gallium oxide for both high power as well as optoelectronic application. Sir, you are requested to now to indulge your lecture. Over to you, sir.
Can you please once again confirm if my slides are visible to you?
Yes, sir.
Yes, sir. Yes, slides.
You can change one or two slides.
Check.
Check. Yes,
Yes,
sir.
sir.
It is fine. Now you can start.
Okay, so thank you for your kind introduction. So, so today I'll as well as thank you to all the INUP team and organizing committee to give us this opportunity to present some of our recent development in deep UV photodetector using this gallium oxide like wide range of semiconductors. So since this is workshop, so I'll go a little slowly and I'll try to keep on defining these different terms and what is this photodetector and how we can achieve a high performance detector. So this is the quick outline of this present talk. Initially, I'll give a broad introduction for this UV photodetectors. Then we'll discuss some of the photodetectors we have developed using low pressure chemical vapor deposition. Will show that how we have initially optimized this wide bandgap semiconductor gallium oxide using this LPCVD. Then how we are using this tin. SN is again is the tin. So how we have incorporated tin as alloy in this gallium oxide wide bandgap semiconductor. Then we'll also show how this SN we incorporated as a dopant. So dopant, doping and alloying two are different. That also we'll discuss, and how they can differ our detector performance also. That also we'll discuss. Then following that, we'll discuss that this SN doped gallium oxide along with this tin oxide, that is SNO2. How we can use this type of heterostructure as a tandem device structure to utilize and get a broad range for detector. So in last topic, we'll discuss the heterojunction based for detector. So this is again three terminal device. That is why the name is the light effect transistor. So this is another very recent work we have done. So that also we'll discuss. So then if we try to define what is a photodetector, again from the name itself we can get it detects light or photon. So again we can consider this photodetector as a transducer which it converts the light energy to our electrical energy. So the working principle of this photodetector one thing I should mention that this auto detector can be achieved in many ways, but mostly focus on the solid state devices. So how can we use the solid state device? There is some noise, it seems.
Yes, sir. I request all the participants to mute their mic, please. So you can continue the session. Okay.
Thank you. So now in this talk, we'll consider this solid state devices, how the solid state devices we can use to detect light or to convert light energy into electrical energy. Now, in very brief, this type of solid state photodetector device operation can be categorized in these three categories. One is the first, of course, the generation of electron hole pairs. That means the carriers by this incidenting photon or the light. And then we need to efficiently separate out those carriers. Otherwise, what will happen if they again recombine, then we may lose the electron hole pairs or the mobile carriers, and we may have to compromise with the device performance. So we have to separate those electron hole pair generated, and in some of the cases we are using some multiplication mechanism to amplify the this number of electron hole pairs generated eventually to get an amplified current. And eventually we need to extract this electron hole pair generated or the charge carriers generated from the electrode to get the output current from the electrode. So if we try to show this three operation, that means generation, separation, and extraction using this quick cartoon. So essentially this is nothing but some photosensitive material deposited on a particular substrate. So this is a photosensitive material, and this is the and then again, if we shine light, so in this case the photon or the light is the UV or the ultraviolet light. So if we shine this UV light on this photosensitive material, so what will happen? So then there will be some electron hole pair generated within this photosensitive material. And then if we deposit electrodes, two electrodes, and apply some bias, then we can separate out those electron hole pair generated. So then generation, separation, and extraction. So now coming to this particular slide, because as I mentioned, these photodetectors we developed, they are all solid state in nature. Now in solid state device discussion, we need to discuss device operation or any operation of these devices using the band diagram. Now let us see how we can use the band diagram or the energy band diagram to discuss this basic mechanism of a photodetector. So then first let us consider this one. So here this is again metal. This is the semiconductor. As you can see, here we have conduction band. This is the valence band, and this is another metal. So then this is under the dark condition and no bias. So that means this particular semiconductor or this device is under thermal equilibrium condition. But still, as we know that even under thermal equilibrium condition also, there will be some thermal energy to take some electron from the valence band to the conduction band, and essentially to provide us some electron hole pairs. But there is no bias, so there is no current. Now, if we go to this this particular band diagram, here this is under non-equilibrium condition. So here still it is under dark. That means there is no photon or light incidenting on this semiconductor. So, but there is some external bias. So since there is external bias or the electric field, there is this band bending in both the conduction band and the valence band. Now, what this biasing will do, so it will give us, it will separate these electron hole pairs. These are again not the electron hole pairs created due to the UV light or the photon. These are the electron hole pair created thermally. The thermal energy is the main reason behind this carrier generation. But if we apply the bias, so we will get the current, and this current is similarly called as a dark current. So after this, if we apply the light, that means here it is UV light. So if we apply light or the shine, the semiconductor is the UV light. So along with the thermally generated electron hole pairs, there will be more number of electron hole pairs generated due to these photons coming or incidentally on this photosensitive material. And now if we apply this bias externally, so we will get the current. And this current here in this photodetector termed as the photocurrent. So this is the basic working principle or mechanism of this photodetector using band diagram. Now coming to the this UV, because the title of this talk is development of UV photodetector or deep UV photodetector. So what is this UV or deep UV? What is this ultraviolet? UV stands for ultraviolet. So this is again, you can see this is just electromagnetic spectrum. So here we have this visible light that is in between 400 nanometer to around 780 nanometer. And below this visible range, we have this range of ultraviolet electromagnetic spectrum. But within this ultraviolet spectrum, our main focus area is the deep ultraviolet region, which is UVC, which is around 250, 254. So this particular region, and why we have chosen this particular portion of the electromagnetic spectrum, that is also like there is also some reason, some justification why we need some photodetector which will be able to detect light in this UVC domain. Now, another interesting fact regarding this particular UVC is typically, the sunlight which is coming on Earth. So the UVC component in this this solar spectrum is very low. Now, if we develop any detector, so that means there will not be too much of noise coming due to the solar spectrum, because the most of the source of this electron light on Earth is the sunlight. So that means this is blind. This type of devices these are the blind to the solar spectrum. So that is why the application or the device development in this region is also very important. So the solar spectrum will not disturb this particular region of electromagnetic spectrum. That is why it is also called solar blind region. Now, again, coming to the application part, since this is solar blind along with the high energy photon, so it has various applications such as monitoring UV sterilizing system, because if you know, I think just we had this COVID pandemic. So during that time, our this UV sanitization this system was almost like a common household system. So to disinfect like your bank these notes and some certain things. So, but this UV sterilizing system, it uses this particular spectrum of electromagnetic spectrum. So that means the UVC region is being used by this disinfection system. Now, another application is the ozone hole detection. As I mentioned, that the sunlight coming to the earth, the UV component is very less, because the reason is there is a ozone layer in the atmosphere, as we know, and that ozone layer is basically absorbing that portion of UV spectrum. So now we know recently, due to the CFC or the carbon fluorocarbon coming from different cooling equipment, so that is creating some ozone hole in the ozone layer. And due to that hole in the ozone layer, so that UV component from the sun may come. So, and which is also very harmful for us, because this UV, if it falls on our skin, there may be probability of getting skin cancer. So that is why this monitoring of this hole in the atmospheric ozone layer is very important, and which we can do using this kind of deep UV photodetector devices. That means simply if there is detected UV light coming from the sunlight, so then perhaps there is some hole formed in the ozone layer. So then we need to take the proper precaution. So then another very important strategic application is the missile plume detection. So in the missile plume, there is some emission of this deep UV spectrum, and if we can efficiently detect this plume, so we can quickly take action against that launched missile. Again, the advantage is because you can guess that when there is this missile launched, then there might be some other type of emission also from different part of the electromagnetic spectrum. But since this UVC is the solar blind, so even if this missile is launched in daylight, so we'll be able to track or detect this missile launch because this is a solar blind. So it can the detector can give us the signal without any faults. So now another type of application is the communication. So, but this communication is again a little bit different. So using this UV light, you can have communication non-line of sight. Why? Because this UV light, again, it scatters a lot, because we know the scattering of light is inversely proportional to the wavelength. Now, since this wavelength is very low, the scattering is very high. And this property of this particular deep UV spectrum enables us to develop communication system using the non-line of sight approach. So this is another very interesting communication or interesting application, which is communication. And another application is the UV astronomy. So here, so we can develop using this kind of photodetector. We can develop an array of devices where which type of devices can take the light coming from the stars under that deep UV region. Because you know, in the normal camera or imaging system, that can only detect the visible spectrum. But there are many stars which is emitting the deep UV light. So anyway, to detect this kind of image, that camera has to be placed in the space. Otherwise, you know, if there is no ozone hole, that is of course not expected. So then the light will not reach to the Earth's surface. So anyway, this is again space application. This is another strategic application. So which can take photo from different stars where the light is coming in the deep UV region. So, but to develop this all UV or deep UV photodetector, we need certain kind of material. Now, which type of material is suitable for developing this kind of application or devices? Now, if we look at this particular chart, here once again there is this electromagnetic spectrum. So then this is the material. So there is a nitride family, and recently this emerging oxide family. So in the nitride family, the algan is again, you may know that this is a ternary nitride semiconductor, and which can be used for detecting this deep UV spectrum. And this gallium oxide and its alloy can also be used to detect this deep UV. Now, why suddenly I'm taking this particular materials so to detect this UV? Because we know that to detect certain light, the photon energy should be more than the band gap of that particular semiconductor. Once again, the photon energy or the light that is coming, the energy of that light should be greater than or equal to the band gap of the material. Otherwise, if it is less than the band gap of the material, then that particular photon will not be absorbed by the photosensitive material. That means that will not be detected by this kind of by the semiconductor. Now, this is the again very simple relation between the energy of photon and the wavelength of the light. So, which also says that this particular material is suitable for detecting the electromagnetic spectrum around 250 nanometer, and the band gap of the semiconductor should be around 5 electron volt. So, this is the reason behind why we are choosing this gallium oxide to develop this kind of deep UV photodetectors. Now, moving on to this type of the photodetector. So here, this is again, this considering the different device structure, we have this type of different photodetectors. So this is a simple photoconductor. Here, simply we have two metal, which is giving ohmic behavior, and we have a photosensitive material. So then we have a Schottky photodiode. Here we have this ohmic contact, two metal, and the third one, this is the Schottky contact. And using this, we can develop Schottky based photodiode. And then this one is MSM. MSM full form is metal semiconductor metal photodiode. So here what happens, this is one Schottky contact, this is another Schottky contact. So this is the semiconducting portion. So that is why it is called metal semiconductor and metal. So MSM photodiode. And we also have this MIS type of structure. So MIS, as the name suggests, it is metal insulated semiconductor photodiode. Then we also have PIN photodiode, that is P-type doped semiconductor, intrinsic semiconductor, and then N-type semiconductor. By combining these three types of semiconductor, we can realize this photodetector. Then this is the three-terminal device, that is transistor. Here we have two ohmic contact, one Schottky contact, and this is the P-type semiconductor. And then also we can realize this bipolar phototransistor. So here we have this is a kind of a BJ. So here we have PNP. So this is a P type. Then this blue one is the N type semiconductor, and again P type semiconductor. So PNP transistor, which is also used to detect the light. That is why it is called the bipolar phototransistor. Now this is a very generic categorization of the photodetector. Now, in case of our this gallium oxide, this is again, although this material has many advantages, but still it has a few disadvantages. So one of them is the non-availability of P-type dopant. So again, I should so this is not the non-availability of P-type dopant. This is actually the material. I think have that slide. So anyway, so even though if we have dopant for making this gallium oxide P-type, but if you know the band structure of this particular material, the valence band structure is almost flat. That means there is no curvature almost at all in the valence band. So it says that even if there is some hole present in the valence band, they will have very high effective mass. Now we know that if the effective mass is very high, so then they will not contribute to the current, or the current, even though there is current, that current will be very small because the holes are heavy. So that is why in case of gallium oxide, it is very difficult to realize p-type gallium oxide because this is the material constant, and now this band structure we cannot change for a particular material. We can change a little bit by applying stress and other things, but this curvature, remarkably, we cannot change. So this is the main limitation for this gallium oxide based technology. So realization of p-type semiconductor. That is why, considering this limitation, so we realized this photodetector using this gallium oxide in this two type of configuration. That is MSM type of photodiode, as well as we have developed some transistor. So, but that transistor is a little different than this one. So that we will discuss. So now again, these are the some figure of merits of photodetector. So as I discussed when discussing the band diagram, so that the dark current is the residual current which flows in absence of any incidenting light. Then there is another figure of merits which is called PDCR, or photo to dark current ratio. So this is simply the ratio between the photocurrent and the dark current. So now another important specification of these photodetectors are the responsivity. That means how much current we are drawing at how much intensity of light. So that is why this is the current divided by the intensity of light. Then we have this detectivity. It says how well a signal can be detected compared to the detector noise. So because again we need to know, as I mentioned, in case of application like missile detection, missile plume detection, so this detectivity of any detector will be very crucial. And the other parameters are like response time. Response times, again, how quickly our photodetector can respond to the light that is incidenting on this photodetectors. So this is again, there are typically this response time. It is divided in two parts. So one is the rise time, another one is the fall time. And this typically this rise time is also divided into two parts. One is the faster rise time, another one is the little slower rise time. And similarly, this fall time or the fall time also divided into two parts: faster fall time and the slower fall time. And different reasons are there behind this different response time that we'll discuss in the coming slide. And another important specification or the figure of merits for this type of photodetectors is the quantum efficiency. There are two types of quantum efficiency. One is the internal quantum efficiency. Another one is the external quantum efficiency. Now, internal quantum efficiency is the ratio of number of electron hole pairs generated by the number of incidenting photons. So, but the external quantum efficiency relates the number of electron hole pairs collected to the number of incident photons incidenting on the sample. So now you see, as I mentioned in the basic working principle of photodetector, because there is a generation, separation, and collection. So this internal quantum efficiency takes care of this number of electron hole pairs generated. So it does not consider whether those generated electron hole pair will be separated and eventually collected or not. So that will be considered in the external quantum efficiency. So that is why these two efficiency, they are different. So the internal quantum efficiency and external quantum efficiency. Now coming to the material part. So why this gallium oxide certainly? So as I mentioned, this gallium oxide, the band gap is suitable to detect this deep UV spectrum of or portion of electromagnetic spectrum, so which has a band gap of around 4.6 to 4.9 electron volt. And then several other important properties of this gallium oxide materials are it has a high electric breakdown electric field. Apart from this photo detection, this material is very promising for developing very high power devices. So again, this is another figure of merit. So this is called Baliga's figure of merit. It says how this material is well suited for power application. And then this gallium oxide material, it shows polymorphism. That means you can realize we can synthesize this particular material in typical this 5 phases. So 5 phases have 5 different crystal structure. As we know that the solid state material has some crystal structure in it, so all the atoms are properly arranged. But this gallium oxide here, these atoms, there are 2 types of atom, as you can see, this gallium atom and oxygen atom. So they can be arranged together in 5 different ways. That is why we can realize or synthesize this material in 5 different phases: alpha, beta, gamma, delta, and epsilon. And interestingly, this beta phase is the most stable phase of this gallium oxide material. So then this material is also radiation hardened material, and this radiation hardened this particular feature of any material is important if you want to use any device or material in space, because you know in space there are a lot of radiation coming, and any device which will develop for the space application, it should be hardened to those kind of radiations. Now again, as I mentioned, that beta is the most stable one out of these all phases. So this beta structure is also this monoclinic structure. So these are the lattice constant of this particular phase of gallium oxide. Now these are all phases of this gallium oxide. So alpha, beta, gamma, delta, and epsilon. And for this detector development, we mostly use this beta phase. Again, that is the most stable phase of gallium oxide. So now moving on, with this device development part. So initially we developed this kind of LPCVD or low pressure chemical vapor deposition setup. So again, you can see this is a very customized system where we purchased all the components separately and assembled together to achieve good quality material. Now this is a cartoon of the previous actual system. Here you can see we have essentially a furnace. Inside furnace we have this board, and within board we are keeping this one of the precursor, that is the gallium, and another precursor, that is the oxygen, we are flowing through MFCs or mass flow controllers, and here that argon gas is also used to carry this oxygen gas efficiently inside this furnace. And under the this particular reactor zone, so at typically 800 degrees centigrade, so this gallium gets evaporated and there is a reaction with the oxygen, and it forms the gallium oxide and get deposited on the substrate. And typically the substrate we used for developing these detectors, there are 2 types. We tried silicon, sapphire, gallium nitride, but in silicon we could not get good quality gallium oxide material. So that is why we developed most of these photodetector devices using either sapphire or gallium nitride. So this is the overall system. Now this is the process flow that we use to develop this material inside this LPCVD setup, and this is the typical temperature profile that we used to develop this gallium oxide. And now, after developing this or depositing this gallium oxide on sapphire, our next task was to characterize or to understand whether we are getting the desired results or not in terms of material. So, or the quality of the material. So here you can see this is a typical X-ray diffraction result, which says not only we achieved or the gallium oxide on the sapphire, but the quality of this gallium oxide was very good. Why these are good? Because you can see, although there are two or three peaks along with the sapphire, that is the substrate peak, so they are all parallel. So 201, 402, and 603. So they are these reflections or these the peaks are coming from the parallel planes. So there is a proper arrangement of atoms, and this particular peak it signifies beta phase of gallium oxide. That means the monoclinic structure of gallium oxide. So here is the that structure of gallium oxide. Now, after achieving this particular X-ray result, we tried to benchmark this result or to understand whether in terms of quality we are getting good or not. Then we compared with the existing the reported result that this our result was not only good, that it's compared to the existing report, it's to some extent is better. Then we tried to understand the surface morphology of this material. So this is the FESM and result. And then we also measured the thickness of this deposited gallium oxide, which is around 300 nanometer. So then after understanding the material quality in terms of crystallinity, so what about the optical properties of this material? Because end of the day, this material we are going to use for optical application, that is photo detection. So here you can see this is a typical UV visible spectroscopy result, where there is a sharp absorption of light or photon around 274 nanometer, which says that this material has a very high band gap of around 4.76 electron volt. So this is again the top law which we derived from this particular UV visible spectroscopy. So then we have also tried to understand the defect dynamics inside this particular material. So this is a photoluminescence spectrum. So here we got some UV emission, which is dominatingly due to the self-trapped holes. As I mentioned, that this gallium oxide has a very unique band structure considering the valence band. So the holes are very heavy. That is why they get strapped. So they cannot move. And due to that, this kind of UV emission is coming in our PL spectrum. Then we also have some PL around 423 nanometer, which is due to the vacancies. Then we have some green emission, which is due to some neutral oxygen sitting in the interstitial of the crystals. And then also we have some emission at the red region, so which is perhaps due to some impurities. Because as I mentioned, this LPCVD setup, it was very inexpensive compared to the other compound semiconductor development technique. So maybe there were some impurities present, and due to that, this kind of red emission is coming. Now, this is the once again the surface morphology. Here we try to understand that if we change the gallium precursor, as I have shown earlier, that inside the furnace we have taken gallium metal itself in a board. So now that gallium metal we have changed from 2 milligram to 5 milligram, 5 milligram to 11, or so on. So by changing this gallium metal, what is the change we are getting in terms of surface morphology? And that we try to understand from this data. So here you can see till 15 milligram of gallium, we could get the smooth surface. But when we increase this gallium to 25 milligram, 40, even higher than that, that is close to 80 milligram. So the surface, on the surface, there is some nanostructure formation. So why this is forming, that also we try to understand. So then what we concluded, that perhaps there is some, this is called escape growth or Stransky growth model. So initially there was layer by layer growth. So and then it was forming some island. So probably this CBD model, or say the CBD deposition, is following this kind of growth model. So then we try to understand what is happening in the crystal quality when we are changing the gallium metal. So here you can see there is as such no change or the shift in the peak. So that means we got beta phase of the gallium, but what we observe, that there is a change in the crystallite size. Here you can see that this is the variation of the crystallite size with the thickness, and this thickness is also varying considering the gallium weight. So that means essentially the crystallite size as well as the thickness is a function of the gallium what we are considering inside the bore. And along with that, the surface morphology is also changing from the thin film to nanostructure when we are considering the higher amount of gallium inside that bore. So now how to what is the mechanism, like how this growth is happening? So then we try to understand that if we consider this this kind of reaction, that gallium and oxygen initially is giving Ga2O, and then with the saturation with the more oxygen, this is forming gallium oxide. So here you can see that initially there was this island. Those islands formed, and then they are getting coalesced. So after coalescence of this island, we are getting the thin film or the smooth surface of gallium oxide. So if we keep on increasing the gallium metal, what is happening? There might be some accumulation of this gallium, which is again maybe due to the gas-based reaction, or there is the saturation of Ga2O compound with the vapor, and which may enable this vapor solid growth. And due to this vapor solid growth, we could get this kind of nano rods. So here you can see this kind of nano structures we could realize when we increase this gallium too much, close to 80 milligrams. So this is the overall observation and the conclusion of this particular growth mechanism of gallium oxide thin film. Then we try to alloy, or try to incorporate tin as alloy in the gallium oxide. So this is the, again, here you can see this is the configuration we used when we tried to dope. So initially, that the previous work which I have shown, there we did not dope. So that is the simple gallium oxide undoped. Here in this particular work, we tried to dope this gallium or form alloy. So because since the gallium oxide is very wide band semiconductor, without incorporating this dopant, you will not get any conductivity, any electrical conductivity. And if you don't get any electrical conductivity, you will not be able to fabricate any devices. So that is why we try to incorporate tin. And this is the configuration inside the furnace which we used to develop this or to incorporate this tin in the gallium oxide. So this is the tin along with the gallium. So these are the precursor, and then there is oxygen coming along with the argon. And then we kept this substrate a little bit far from this board, and where this substrate is again we use mostly gallium nitride and sulfur. So here we got the SN alloyed gallium oxide deposit. So these are the process parameters which we optimized to get this SN alloyed gallium oxide, and this is the surface morphology. And here you can see why I mentioned that this is a SN alloyed, because you can see here this is the comparison. This red color shows the this after incorporation of tin. So this is the X-ray or XRD data or X-ray spectrum, and then blue one is the gallium oxide without tin incorporation. Now here we can see in this 6bar03 this peak, there is a shift. So this peak shift signifies that there is a formation of alloy. So when we try to incorporate tin in the gallium oxide to modulate the conductivity. So again, there was some nanostructure also formed on the surface, because again, tin is very difficult to manage because tin has some surfactant effect. So due to that, we also observe there is some SnO2 formed on the surface of the gallium oxide. So this is the once again that top plot derived from the UV visible spectroscopy. Here also you can see that in case of this tin incorporation, there is a shift in the band gap. So reduction in the band gap from 4.4 to 3.67. So now here you can see we try to fabricate some devices. So this is again some of the initial device results. So here we deposited platinum on this SN alloyed gallium oxide. So this is the electrical characterization result or the IV plot. So here you can see this is the dark current, and then when we are shining light of 254 nanometer wavelength, then there is a drastic change in the current. This current again, this is a semi-log plot. So the dark current was of the order of 10 to the power minus 11 ampere, from 10 to the power minus 11 ampere to 10 to the power minus 7 ampere. So that means almost close to 10 to the power 6 times change in the current when we are shining the light. So there is another observation from this particular plot. That means, see here at this zero bias, there is a detection. So that means even if we don't apply any bias, our detector will be able to detect the this UV light. So and this is called your self-biased detector. And this is again coming or this zero bias operation is coming due to the some charge trap within the material, as well as there is asymmetricity in this contact form on the gallium oxide. So that we'll discuss soon. So this is again another characterization result. So here you can see this is the time response of this particular detector. So how quickly our detector can respond to the light. And another interesting observation is this device performance is stable. So even after here, I guess there will be 40 to 50 cycles, still there is no drift in the on current. So this is on and off. So that means this type of detectors, they are also stable. And but the everything is not good, of course. This lifetime and the decay time of all time, if you notice, it is of the order of second, which is also not something desirable, because if we again take that missile detection application, our missiles should be detected immediately after it is launched. Otherwise, there will be some destruction. So in that context, this rise time should be very small. So that is the main the or this particular device. So this is another characteristic which shows how with the voltage this current or the response time is varying, and this is the summary of the.
और फिर अब हमने तो क्या करें हमने मतलब बहुत कोशिश की कहीं ना कहीं से एंट्री अंदर.
Okay. So again, as
Ankush sir, you are muted for some reason. Can you try and unmute yourself? Ankush, can you hear me? Yeah, so he probably heard me.
hello.
Yeah, now we can hear you. Thank you. Thank you. Yeah.
Don't know what's happening.
So some participant actually unmuted and we had to mute the participant, and whenever we are doing this, there is some technical issue and the speaker is also getting muted.
Okay, fine. Now shall I continue?
Sorry. Yeah, please continue. Sorry about that. Yes.
So in due to this asymmetricity in the barrier height, although both are formed with the platinum, but due to this self-trapped hole impact, there is this asymmetry in the barrier height. So, and due to this asymmetry in the barrier height, we are getting this kind of self-bias operation. So, without applying any bias also, we can separate out the electron hole pairs and get the photocurrent. So, again, some of the other reason behind this high detection or behind this high performance operation with this. Hello, can I call you back after some time? Ankush? No, I'll call you back. Okay, sorry about that. So, again, the reason behind this high performance is the platinum electrodes, because here this platinum electrodes, due to the high barrier height, the dark to photocurrent ratio is very high. So as I mentioned, this is almost close to 10 to the power 6. So this height, because high barrier height will reduce the dark current. And now when coming to the photocurrent, that is after shining the light, this platinum is transparent, so or the semi-transparent. So that is also the high photocurrent. So due to this advantage of platinum, both high barrier height along with the high transparency, so we are getting this high photo to dark current ratio for this particular devices. So then this is the again benchmarking of this device. After this alloying, we try to dope. So alloying means, again, if we have observed there is a shift in the XRD peaks. That is why there is a significant incorporation of tin. Now we have tried to dope this. So if we consider the doping, that means that doping level is typically of the order of 10 to the power 16 per centimeter cube or 10 to the power 16, 17. So the incorporated atoms, tin atoms, are far less when we consider this tin as a doping. But when we consider tin as the alloy, so the incorporated tin atoms will be much more. So this is the difference between formation of alloy and the doping. So then we tried to see whether we can dope this, because as I mentioned, that managing this tin as a dopant or alloy from atom was very difficult. So then, after a lot of iteration, we could dope this, not the alloy. So, but what we observed that after doping, there is this change in the surface morphology. If we remember that without tin incorporation, the surface was almost smooth, but after incorporating this tin, you can see the surface is becoming rough, and some texture, triangular texture are coming. So again, this surface is becoming more rough with the higher tin incorporation. You can see this tin incorporation is increasing when we, so from 10 to 20 to 30 to 40 to 50. So, and the surface is becoming more rough. So compared to the previous photoreceptor, here we have to.
So there's another 5 more minutes remaining.
Okay. So here we tried to fabricate our devices using the lithography. So here you can see, so initially we cleaned the substrate, then we deposited beta gallium oxide, doped with the tin, and then we have developed some pattern. This is a typical IDE electrode. So then we deposited platinum and we got the photodetector device as IDE. So then this is the electrical characterization result. So here you can see after doping, there is again drastic change from the dark current to the photocurrent. So here we try to understand what is the role of tin as a dopant. So what is happening if we increase the tin concentration as a dopant? So here you can see this is also again with the change in the intensity. Okay, sorry, just sorry. So overall, this is the dark current. So overall, this is the dark current. So this is without doping with the tin, and this is the dark current again after doping. So these are all dark current. Now, after shining light with this 370 microwatt per centimeter square deep UV light, that is 254 nanometer. So this is the response. So this one is the sample without tin doping, and this is after tin doping. So here our objective is to understand what is the role of tin doping in photodetector performance. Because if we increase the tin doping, it will increase not only the photocurrent, it will also increase the dark current. So because here you can see the dark current increased drastically when we incorporated the tin. But it also helps us in getting the higher photocurrent also. Here also you can see this is the current without tin doping, and these are the current after doping with the tin. So how to choose the doping, or what is the optimal point? So here also you can see similar to this dark current and photocurrent. This is the change in the dark current photocurrent with the tin wave, and here the photo to dark current ratio and photo and your responsivity variation with the tin. Now we can observe from here that with the increase in the tin doping, the PDCR reduces, photo to dark current reduces, because photo to dark current is a ratio. So if this dark current is increasing rapidly compared to the photocurrent, so overall ratio will reduce. So, but our objective in getting good high performance device is to increase the ratio. But in that case, we can comment that there should be a trade-off when doping with the tin, because too much of doping will increase the dark current, and that will eventually reduce the performance of our device. Then also we try to understand with the intensity how this photocurrent is increasing. Now in this study, there is some mathematical fitting is there. So this fit, or the exponent of this power, this P is the power of the light shining. So this exponent of this power says about the operation of these devices. So this exponent in case of ideal photodetector is 1. But if there is any trap related photoconduction or current conduction, then the exponent will be lower than the 1. Now you can see here when this steam doping is increased from 0 to 10, 25, 30, 40. So the exponent is decreasing. That means in our device, the current conduction is becoming more trap dominating when we are increasing the steam more. So then again, there should be some optimal point for this steam incorporation. Otherwise, we may get very, like, if we keep on increasing the steam, our performance may deteriorate. So anyway, so I think should I continue or should I have a few more slides? So anyway, I will quickly then continue. So this is the heterostructure or hybrid structure. Here you can see we have combination of both the nanostructure as well as the thin film. So this is the typical tandem structure if we want to realize broad range detection, because gallium oxide will absorb the high energy photon, low energy photon will not be absorbed, will go to the SNO2 and will be absorbed in the SNO2. So eventually we'll get very high broad range detection using this combination. But in case of this gallium oxide, it is difficult to realize this gallium oxide on top of tin oxide. So then what we did, we used this SNO2 nanostructure on the gallium oxide. So because in normal or if we develop the thin film of SNO2 on the gallium oxide, so then high energy photon may not be able to go to the gallium oxide. So then the detection performance may have to be compromised. But if we use this SNO2 as a nanostructure, so here you can see the high energy photons are still going up to the gallium oxide, and low energy photon is getting absorbed with the SNO2 nanostructure. So with this kind of inverted structure, along with this nanostructure form on the surface of the gallium oxide, we can achieve the broad range. So after understanding this mechanism, we tried to realize using this gallium oxide, and we observed that yes, there is a range, there is an increment in the detection range. So this is, again, I am not explaining. So this is already a published paper also. So here we have shown that we can not only get the high response, we can also extend the detection range. So here you can say that the detection range now got extended from 254 nanometer to 302 nanometer. So this is the, and again, last this is a transistor. I will quickly will take 1 minute. So this is the normal transistor. As we know, this is a MOSFET. So here we have the 3 electrical contact, source, drain, and the gate. And if we apply voltage, we will get the channel on and the transistor works, typical MOSFET. But we realized a light effect transistor where we have the 2 terminal as a source and drain as electrical contact, but we have the 3rd terminal which is controlled by the light. So there is no electrical contact like gate, but the control is coming purely due to the light. So here we utilize any different substrate, unlike the previous study. Here we have used the p-type gallium nitride. So again, this is the process parameters which is optimized after a lot of iteration. So this is the surface morphology. This is the XRD plot. So I'll quickly elaborate the device operation. So this is how we are getting the Schottky contact, and here we have tried to understand whether we are getting the p-n junction behavior or not. because both are the short ohmic contact on N-type gallium oxide and P-type gallium oxide, and here we are getting this kind of rectifying behavior. Now this is the transistor behavior. So this is once again there is no gate terminal physical electrical contact. Here the change, as we know that this is the VDS, this is the ideal, and the change here is due to the intensity of light. And the interesting observation here is, which is not observed in most of the phototransistors, this saturation. So because we know that saturation in MOSFET plays a crucial role for both analog and digital application. If there is no saturation, then there will be a lot of problem in MOSFET, I'm saying. So the same saturation is achieved in case of this light effect transistor also. So that means this kind of phototransistor can also replace the analog and digital application. So here you can see these are the, again, sort of similar study, that photo to dark current ratio and how the responsibility is changing. I'll just quickly discuss this particular graph. Here, this is the optical power, and this red color, this is the photocurrent in the log, and this is the photocurrent in the linear. So, and another interesting thing is the GM. So because as I mentioned, there is no physical gate contact, electrical contact. The third terminal or the control is coming due to the optical illumination. And that is why this optical power is similar to the VG or the gate bias in normal MOSFET. Now this optical power or the VG versus this is the GM. And GM also, you know, in typical MOSFET, it is not flat. If it is not flat, then there is a problem of non-linearity. If you use MOSFET as an amplifier, so then there will be a lot of harmonics coming after amplification. But you can see here in this kind of light effect transistor, the GM is flat. GM is meant, that means the gain is fixed with the optical power. So if you use this kind of optical transistor or the transistor for optical amplification, will not get harmonics after amplifying certain signal. So this is the uniqueness of this particular study. So anyway, this is again time response of this particular devices. Here we use this control plot or the simulation to understand how we are getting this kind of saturation, and which is so promising for typical analog and digital application. So here I'll just quickly suggest, see this particular non-equilibrium condition. So this is the electric field contour. So here you can see in normal MOSFET, as we know, the saturation comes due to the pinch off. As the channel gets pinch off towards the drain side, we get saturation in the MOSFET. Similar pinch off is happening in this kind of phototransistor. There is no electrical contact or gate contact, physical contact on this gate side. So this channel is getting pinched due to the formation of PN junction here. So this is the N-type gallium oxide, this is the P-type gallium nitride. And due to the, again, interaction with the other electric field, we are getting the similar pinch off like MOSFET. And this pinch off, again, here, this is in terms of carrier concentration. Due to the pinch off in the channel, we are getting the saturation. And due to the saturation, this type of light effect transistor is very promising, once again, for this typical digital and analog application. So this is again the conclusion of this particular talk. So this LPCVD very promising, and we can realize not only thin film, also nanostructure, and also we can get very high responsibility dark currents, but there will be a trade-off. So again, finally, in acknowledgement, so this is the work mostly done by the PhD student Arnav. Finally, I should also acknowledge all the funding support I received from IIT Guwahati, IIT Mandip, and Ministry of Education, as well as the DST. So with this, I would like to thank you for your kind attention. I'll be happy to address your queries if you have. Thank you.
Thank you, sir, for your delightful session. Sir, there are a number of questions in the chat box. As we are running out of time, You can answer the answer of the queries in the chat box. Thank you again.
Okay, okay. Thank you. I'll try to address as far as possible.
Yes, sir. Yes, sir. Sure. Thank you.
Okay, thank you, and sorry, but it took a little bit longer time. Okay, thank you.
Now I will thank all the participants for attending today's session. Tomorrow, the session will start from 9 a.m. And those who have technical issues while downloading the LAOS software can please wait or can ask right now. You will have help from the technical side. Himanshu, are you there?
Can you hear me, ma'am?
Yeah, I can hear you, Himanshu. So, if any students, any participants had any technical issues to whom the software license were given, can you please ask?
So we have shared two instruction manuals for SCAPES and Laos yesterday. So those whoever has tried and installed the software and successfully and it is working in their system, then it's fine. So they can leave the meeting. Others who are having any technical issue, so they can unmute themselves and or maybe they can share their screen so that we can help them to figure out their problems.
So, sir, your sharing screen is open. You can stop it from sharing. Now it's fine.
And participants, those who have no issues with the Laos software downloading of the license can leave. Anybody else, can you please acknowledge if you have any issues?
Yes, sir. So what is the interface showing?
Sorry, I didn't get you. Can you please repeat?
Can you repeat your doubt, please?
Yes, ma'am. What the interface the software license is showing?
Okay, so this is so this will be solved after you install the licenses. Actually, there are a very limited number of licenses, so we are going to distribute those licenses to only a few participants for the time being. But all the participants can access this license once this live session is over. So we'll send a mail along with these licenses and required instructions for installing the licenses to some of the participants now, and for others after the live demonstration session.
Yeah.
For Laos who are getting this error screen, that means your installation is done. Only thing is required is the license, which will be shared in due time. Yeah, Tejaswini has raised.
So can the both license software can run simultaneously or a different way?
Yeah, they are different tools. For SCAPS, you do not need any license. It is a free software. And for Laos, you need the license. But yes, if your system is capable, then you can run both the systems together, both the softwares together.
Hello.
Yeah. Yes.
Sir, I have installed both softwares, Escapes 1D and Log software. Sir, currently I am working in the Escapes software. So, sir, the same device, actually, I am working in the CIJ Solar Cell Technology. So, can you simulate my device in the Log software?
Uh, yeah. Laos is basically is used for solar cell devices only. But in this session, we'll be discussing only like the problems regarding the installation and download. So we'll be discussing details about this, the working of the softwares and their capability in the tomorrow's sessions.
Okay, sir. Okay.
Yeah.
Uh,
Yeah. Whoever
Sir,
has raised
actually,
their hand, you can. Yeah. Yeah. Go ahead.
I downloaded the software SCARPS, but
Okay.
after completing all the processes, lastly, it is showing that no software will be installed or removed at the installation summary.
Yeah. So I think somebody has mailed me. Have you mailed me like showing a screenshot of this thing?
No, sir.
Okay. So have you used any previous version of SCAPS in your system?
No, sir. It's first time.
Mm, okay. So mostly that error is coming for like for those people who have used some previous version of SCAPS. Uh,
Okay. At first, it
so
actually completed, means at first time when I downloaded it, the installation process was completely done. But for one
okay.
moment, it got lost.
Okay. So installation was completed in the first try.
Yes, sir. But for a fraction of second,
Okay.
it actually got lost, sir. Again, it showed no software will be installed.
No, no. Like after completion of the first try, so it is not the software is not working.
No, sir. When I actually installed, no, at that time I
Yeah.
completed the whole process, and lastly,
Hmm.
it showed the your finished process was finished, and
Yeah. So
but
I think
after
we
fraction
are
of second, it again started to showing that no software will be installed.
no. So once the installation is completed, you don't need to this run that setup file once again.
Okay.
So you just need to go to the problem is that this software doesn't create a shortcut in the desktop directly. So you have to
Okay.
go to the your installation folder. Maybe mostly in normal cases it is in the C drive, and
Okay.
you go to the program files and find the SCAPS folder. In that SCAPS folder, you will find a icon called SCAPS 3311.
Okay.
You have to run that file, not the setup file once again.
Okay. Okay. Sir.
So you go to the C drive and you will find that icon.
Okay, sir.
Yeah,
Thank you, sir.
yeah. Deepa, Miss Deepa, whoever has raised their hand, you can unmute and ask your questions. It's just Srini. Yeah, please. I'm not able to hear. Yes.
So regarding the Lavis software, when will be given the license key, sir?
Yeah, license actually that we are distributing, but the problem is that there are very minimum, a few number of licenses. So we can distribute those licenses only to a handful number of participants, at least for the live session. So those who will get the licenses, they can use the software during the live session. But uh, for those people who will not receive their license before like tomorrow sessions, they will get the license after the session, so they can use it for 1 week after the uh, workshop. So whatever you have learned during that demonstration session, you can try it in the software after the workshop.
Okay, so to limited people only right now you are giving, sir?
Yeah, unfortunately, the company like according to their policy, they cannot provide that many number of licenses. So
But
we
after
can,
the once the means 1 week license will be for all the
yeah,
participants or
for
only for you?
like number of licenses will be same, but all the we will distribute those licenses to everyone, so you can access it in your convenient time. And the recordings of these demonstration sessions will be there, so you can refer to those recordings and use the software.
Okay, sir. So
And
okay, sir.
as
Thank you
a,
so much.
and I was I was discussing with the company personnel. They said if somebody is really interested in the software, he is ready to give some trial period license for that. In that case, so you can contact the
Yeah,
company
yeah.
person for that.
Okay, okay, sir. Because we are the faculty here, because I hope so. If you give the more license to the faculty participants, then they can teach for the other scholars or other PG students further. If you give the preference to faculty generally. Okay, that is
Yeah,
your
that
wish.
actually we are
You please
figuring
think
out.
about that. Yeah, because
Yeah,
all
we'll,
participants are important, because all need to be have their hands-on training. But
no,
so
you can
that's
attend the session.
okay. Okay. Mm.
Yeah,
Okay.
we'll try to
So
like give as many numbers as possible.
okay, sir. Thank you so much.
Hello, sir.
Yeah,
Sir, after installing the LOS license software,
yeah,
error shows. Sir, there is prompt open that say the fix some supports.
yeah. That if your this error message is coming, which says that contact Fluxim support,
Yes, sir.
then it's okay. Like once you install the license file, your software will work normally. That is not the problem. So if in case of Laos, the last step for you at this point of time is to get that error message only. So
So what we do, sir?
so if you have reached that point, then okay, it's fine. You can attend the session tomorrow. Once you activate the license, then you can you can do the hands-on demonstration during the tomorrow's live session. For the time being, it's okay, fine. You can leave the meeting.
Yeah.
Yeah, Mr. Arvind, you have raised your hand. Please.
सर can screen share कर सकते हैं अपनी?
Yeah, whoever has raised their hand, you can ask your unmute yourself and ask your questions. But I'm not able to hear. Arvind, if you are saying something, I'm not able to hear. Yeah, Arvind, is this?
Hello, sir.
Yeah, just a second, Arvind. I think this is your screen that you have shared. I'm not able to hear, but I think you are after the installation, you are again trying to open the software from the setup file itself. So you do not do that. You go to your installation folder, which is mostly in the C drive, and find a SCAPS folder in the program files and run it from that folder.
Okay.
Yeah, Ms. Deepa.
Hello, sir. I have a doubt. Like this software which you have given. So, how like does it work for like longer chain molecule? And can we try interrupting or just fabricating it?
Yeah, this software actually for this SCAPS is used for solar cell devices using any type of material. You can introduce any type of material, and LAOS is also used for large area devices. So it is not material specific, but yes, you can use it. But the details of this software and their capability we will discuss tomorrow in the respective sessions. You attend that session. You can the doubt will be solved.
But today you are just showing us like how to open or access the software,
Just
right?
just how to whether you are successfully able to download it and install it or not. Because tomorrow during the tomorrow session, while these softwares will be demonstrated, you can do hands-on parallelly.
Okay, sir. Okay. Thank you, sir. Sir, I'm working on polymer. So polymer can be simulated in this app?
No, this is not a material. This material simulation. This is a device simulation software. Devices using any
Okay.
material, you can simulate.
Okay. Okay, sir. Thank you.
Yeah. Yeah, for those who doesn't have any issue like while downloading an installation, they can leave the meeting. The today's session is over. You can join tomorrow. Yeah, I think nobody has any more doubt. So if you have any other doubt, like okay, Mr. Sumit. Yeah, yeah, Mr. Sumit. So
Yes, sir.
so what I think
Yeah,
what you are trying after the installation, you are trying to
yeah.
open the software from the same setup file. So
No, no, no.
you
This
don't
is
need to
not my screen. I think someone else has shared this.
okay. Tejaswini, just a second. Tejaswini, I'm not able to hear you, but I think what you are trying to do, after the installation, you are trying to open the software from the setup file itself. So you don't need to do that. You have to go to the installation folder, which is mostly in the C drive, or go to the program files, look for the SCAPS folder, and open the software from that folder. Yeah, Mr. Sumit.
Yes, sir. Yes, sir. As in the recent mail, you have provided a step to
Yeah,
activate the LAOS license. So
yeah,
at
yeah.
the last step 5, I was trying to submit, but it is not submitting that
Yeah,
submit
so
button.
you just
Yes,
need
sir.
to click it. You will not see any new screen. So if you have done the previous steps correctly and you click submit, then it will work. Then after that, when you open the Fluxim, LAOS will open.
Okay, okay, okay. So means it will not show any dialog
Yeah,
box
it
or
will
any
not show
confirmation
any new
like.
dialog or any new screen. Yeah, you just need to click it.
Okay, I clicked it several times, but I soon
Yeah,
I
yeah,
was
I
thinking
get.
that nothing is happening. That's why I was.
Yeah, no. You just
Okay,
try to open the LAOS software. It will work.
okay, okay. I just try. Just wait. Yeah, it is opening. The screen is opening
Yeah,
right now.
yeah. Thank
Okay, okay, sir. Thank you, sir.
I think no one is having any more doubts. So if you have any like issue for this installation and download, so you can reply to the mail that you have received yesterday. So just do not reply to all. Just reply to the one who has sent you the mail. Okay. So we'll contact you and we will try to help you for the installation. Hello, ma'am. Emily, ma'am, are you there?
Himanshu, it's me, Rajan. Tell me.
Yeah, well, sir, I think no, everyone. I mean, we have addressed everyone's queries, so I think there is no more doubt or any issue. I think
Okay, so
we
I'm
can end the meeting.
okay. Should I shut down the meeting?
Yeah, I think nobody's asking any check in there.
Wait for another 5 minutes or?
Yeah, sure. We'll wait for another 5 minutes. I think Ankush Bag sir has posted a message. So if you have any questions for Ankush Bag sir, so you can post it here.
Okay, we are going to wait for 5 minutes till 5:45,
Yeah,
and then I will log out the meeting. Okay.
yeah, sure.
Thank you. Himanshu.
Yeah, yes, Rajan sir.
I'm going to switch off the meeting. Okay.
Yeah, sure. Thank you. See you tomorrow.
Thank you. Bye bye.